Okay, so we're going to do a quick video that explains how the bucket diagram chart works for Inulin, specifically for the Paul L. Foster School of Medicine Year 2 kidney test. So if you remember Inulin and creatinine are very similar, and Inulin is used because it is something that's found in the blood, not naturally, but you can put it in the blood, and it's fully secreted but is not reabsorbed. And creatinine is close to inulin. It's found in the blood naturally, and so it's a close estimate of what you would get with inulin, and it can be used to calculate the glomerular filtration rate. And then you don't have to inject the patient with anything. So we're going to go ahead and use inulin now because it makes the calculations easier, and then you can remember that creatinine will be pretty close. For these bucket diagrams, we like to use this chart that Dr. Jansen made for his book Bucket Diagrams, and we'll just take a quick look at the chart. At the beginning here, you have the afferent arteriole here, and it comes in, and the capillaries here enter Bowman's space. Part of what was in the afferent arteriole bucket, or part of this blood, gets filtered into Bowman's space. The part that doesn't get filtered stays in the capillary and exits with the efferent arteriole. Now, if you just stay with the efferent arteriole here, it will keep going into the peritubular capillaries, and then it will go out here into the renal vein and it'll be gone. So this is one circuit. Afferent arteriole, some of it goes out here, goes through the efferent arteriole, proximal convoluted tubule, peritubular capillaries, and then out to the renal vein. Now, what about the fluid that left and entered the Bowman space? Well, the fluid that left and entered Bowman's space goes here into the proximal convoluted tubule, which this part is labeled P3. It's one of his favorite buckets. Then the loop of Henle here, the thick ascending limb, the distal tubule, and then the collecting duct here. So for a test question, you might be given something like this, and he has to give you a couple values to start with, and then you calculate the rest. So what we have here is we start here with the number 500. So this is our amount. And so the amount here is talking about the amount of drug or chemical that we're calculating. And so we have 500 milligrams per minute moving through, milligrams per minute, traveling through here. And so if we start out in the afferent arteriole and we have 500, and then it enters here into Bowman's space, normally we will filter out a specific percentage. And for inulin, we always will get about 20%. And if you look here, because inulin is not secreted and not resorbed, you just get whatever comes out in that 20%. What goes out in the urine left here. Nothing else changes. Nothing secreted, nothing was resorbed. So what left here ends up in the urine. So we look at our urine amount, and it was 100. So that means that the 100 that we get in the urine had to have come out here. So out of the 500 that came in, 100 came into Bowman's space. And if we look at the calculation, 100 divided by 500 is 20%. Okay, so that's like a double check. It makes sense with what came out in the urine, and it's a 20% that was filtered, so that's perfect. Now, if we think about it, if 20% came out here, which was 100 milligrams, how much is left? Well, 500 came in, 100 left. That means 400 had to stay in the capillaries. So in the efferent arteriole, you've got 400, which makes sense, right? We have 500 coming in, 100 went into Bowman's space because of the 20% filtration, and then the other 400 went out. Now, in P3 here, what do we have? Well, we had 100 in Bowman's space. What's Bowman's space connected to? The next bucket is P3. So if we had 100, it's going to stay 100, but because it's inulin. Other things might be different, but because it's inulin, it's not secreted, it's not resorbed, it stays the same. It's still 100 at P3. Now, what about PC, the peritubular capillaries? Remember, that's not in the nephron. This is a capillary that's connected to the efferent arteriole. How much was in the efferent arteriole? That was the 400 that was left that never got filtered out, and it's still in there. So that's still 400. We had 500, took 100 out, we had 400, 400 stays in. So we've still got 400 here. And then same capillaries turned into the renal vein. So if we had 400, we're not secreting it, we're not absorbing it, stays in there, 400, still 400. So that's our first chart for the amount. Now we can look at the flow. So the flow is more, you can think about it like the water that was in there. So originally, we're given this concentration of 1. If we have a concentration of 1, if we have 500 milligrams of the drug or the chemical, how many milliliters do we have to get a 1 concentration of milligrams to milliliters? It has to be the same, right? For a 1 concentration, 500 milligrams per 500 milliliters would be a concentration of 1. So this has to be 500. If this number were different, we would change this number. Because it's 1, it's an easy calculation. So luckily, that's going to be a 1. Now, we know that we filtered out 100 milligrams, and we were at a 1 concentration. So that means we took literally just 20% of the fluid and the drug. And so we took the exact same amount of water out, because here we're not doing any resorbing or any secreting. We're just taking out 100 at a 1 concentration. So we still have 100, which means our concentration is still 1. We don't change the concentration in Bowman space. And same thing, what stayed? Well, remember we left 400 of the drug, and the concentration still doesn't change. Nothing in this part of the kidney changes the concentration of Bowman space. So we've still got a concentration of 1, which means that up here we would have 400 milliliters of fluid. So the exact same thing that happened with the drug is happening with the fluid, because our concentrations aren't changing yet. But when we get to P3, this is where things get a little bit different. So in P3, we resorb 2/3 of the water. That's just standard. And how much water did we have going towards P3? Well, we started with 100 that we took into Bowman space at a concentration of 1, which meant we have 100 milligrams of drug and 100 milliliters of fluid at a 1 concentration. If we have 100 and we resorb 2/3, what is 2/3? So if we do times 0.66, we resorb 66 milliliters of water, which leaves us with like about 33. We're just going to do 33. That's how much water is left, because we resorbed 2/3. Did we resorb any inulin? No. Inulin is not resorbed and not secreted. So the inulin amount stays 100, but the water is less. So we increased the concentration. By how much? We tripled it, because same amount of inulin in 1/3 of water means 3 times as concentrated, right? So if you take the 100 here and divide it by 33, you'll see the 3 concentration. Okay, so that's where you get the 33. Now, where did that water go? It doesn't just evaporate. It was absorbed into the peritubular capillaries. So how much water was in there? Well, go back a step to the EFF. It had 400. We just resorbed 2/3 of the 100. So that 66 or 67 that we resorbed had to go into these capillaries. So that would be the 400 that was already coming to the peritubular capillaries from the efferent arteriole is now going to have an extra 67 in it. So that's where we get 467, because it can't go anywhere else. If the 100's not in here, it has to, most of it or 2/3 of it exactly had to go in there. And then what's the next step? Well, we can... Okay, so we had a small phone issue, but we're back. Just to recap, we were on the concentration here, and at P3, this bucket, we had 100 milligrams per minute, so milligrams that came out of inulin, and now it's only in 33 milliliters of fluid because we resorbed 2/3, and so 100 divided by 33 is 3. So that's where we get this concentration of 3. And then we were going to jump down to the urine, and we said that the urine here, we're given, only excretes 1 milliliter of fluid. So if we only have 1 milliliter of fluid that's excreted, even though we had 100 milliliters come into Bowman space, some way or the other, it's mostly has to be resorbed back into the body, into the capillaries. So all of that 100, we're down to 1. So that means 99 of it left. We had already taken 67 out, but one way or another, we were going to get the other 99. So we get 499 here, because 499 plus 1 is 500. We started at 500. Only one's leaving the system through this tube. That's the only other way it can leave. So that's where we get the 499. Now if we look at the concentration again, we have 400 now in here with 499 of fluid. And so what is the concentration over here is 0.8. So over here we have 0.8 left. That kind of makes sense because we filtered 0.2, 20%, and all of that amount went out in the urine. But here we have the other 80%, 0.8. So 20% went in this tube, 80% went in this tube. That makes sense. But as far as the water is concerned, 1 milliliter went out here, and the other 499 milliliters went out here. So this concentration is 0.8. My pen will work. Okay, now if we look at the last line here, urine, we have the 100 came out in the urine, that was given, and only 100 milliliters of water. So this is the most concentrated of everything. So 100 divided by 1 is 100. So this is completely concentrated at 100, very, very concentrated. Now what is this TP over P? Well, first of all, TP is a typo. It should be TF, tubular fluid divided by plasma. And I like to think of this as concentrations because this is a ratio of concentration. So I'm just going to write that in a concentration bracket. So TF over P. So tubular fluid over the plasma. Now what represents the plasma? The plasma is pretty much what you got when you started. The afferent arteriole is the plasma. And that's the bottom part, the denominator. The numerator here, tubular fluid, well, which tube? The tube you're on the line of. So this would be the BS tube because that's the line you're on. That one's blank, forget it. This one, what is this tube? P3, that's the one you're on, it's the P3 tube. And this one, that's the U tube. So pretty much the TP stands for what line you're on, and the P stands for AFF. So TP would be BS, and P would be AFF. So this is BS over AFF. So BS is 1, AFF is 1, because these are concentrations. 1 over 1 is 1. So this is the ratio of these concentrations is 1. Now let's look at this one. Which tubular fluid line are we on? P3. Well, what's the concentration in P3? It's 3. Divided by the plasma. Which one was the plasma? The first one. 3 over 1 is what? 3. Those are the ratio of those concentrations. All right, now down here. Tubular fluid in the urine. Well, what's the concentration in the urine? 100. Over P, what was P? AFF. 1. 100 concentration over 1 concentration is 100. So this is just a ratio of the concentrations. And that's it for inulin. One other important thing that we need to mention before we finish talking about inulin is that the reason we use inulin is to calculate the GFR, or glomerular filtration rate, and the important number is right here, 100 milliliters per minute, because this line is Bowman space and showing us the flow. And this number is only 100 if you use inulin to do these calculations. If you're using another chemical or another compound or another drug, this isn't necessarily going to be 100. But when you use inulin, when you look at this box, whatever number you end up with is your GFR. So 100 milliliters per minute, 500 milliliters came through the afferent arteriole, 100 of it came through into the Bowman space. So your glomerulus is filtering 100 milliliters per minute. That's your GFR. You can just remember right here. This is always your GFR for inulin calculations. 100 milliliters per minute. If you get other numbers, then you know your GFR is low or high or whatnot, especially clinically if you can do this and figure everything out. That's your box. So if you have a test question and you have to do all these calculations and it says what's the GFR, you look right here because you remember out of the 500 you got 100 into the Bowman space, and you can calculate it because the inulin stays where it's supposed to and comes all the way out, and the calculations work. With other compounds, you will get a different number. So 100 GFR, which, as we mentioned earlier, 100 over 500 is a 20% ratio. So that's also standard in a regular patient.